Okay, as promised, here's the next video on ladders, looking at extending it to a couple of slightly more complicated questions. But let's start with a simple one. In fact, I hope lots of you will have done this when you revised for the recent assessment. We're on page 162 in the motorbike book, and question 2 here, so screenshot that if you haven't got the book. I'm going to walk you through this one. So it's, a good diagram, always important, so here we go. It's always important to read carefully. So we've got a rough wall, so we have got friction, a smooth ground, so there's no friction here. There are a couple of forces here, but not friction. With a ladder, we've always got two reaction forces, always perpendicular to the ground and the wall. So we've got one here, which I'm calling R, and one here, which I'm calling N. There's an extra force that's being applied. We're told that this force is holding the ladder in limiting equilibrium. It's 35 newtons. But the ladder is about to slide up the wall, not down the wall. So that's why friction, which always opposes movement, is coming down here. And because it's on the point of moving, sorry, I've been painting, it's on the point of moving, we know that friction is at its maximum value. It's, it's F lim, F max, sometimes they refer to this as, and that's mu times the size of the reaction force, but of course I'm calling that N, so it's that. And these ladder questions we always do as 3 steps. We resolve vertically and horizontally, not parallel to the ladder, and perpendicular to the ladder. It's not a slope question. So when you've got an object sliding up and down a slope, we tend to go parallel and perpendicular, but no, here we tend to go vertical and horizontal, and then we take moments, and we normally do moments about the base, because there's often a lot of forces here, and if we do moments about this point, then those forces have a distance of 0, so we can ignore them. So I've gone. Well, I'll tell you what. Why don't you do this step here first? So resolve vertically and horizontally. See what that tells you. Then we'll talk a little bit about the moments. Okay. So here's what I got. So going vertically, I've got the reaction force from the ground. I've got the weight of the ladder, and it's uniform, so that's acting at the midpoint, 3.5 meters up, and I've got the friction force there as well. So forces up, equal forces down, because it's in equilibrium. Resolving horizontally, I've only got 2 forces acting horizontally. I've got the 35 Newton force, and I've got the reaction force, so they've got to be equal to each other. And because I know this, I'm in a pretty good position here, in that I'm getting close to working out either F or coefficient of friction. I know what N is, and in fact that's part A, the magnitude of the normal reaction of the wall on the ladder. So part A is 35. So okay, so we've done that. Now we're going to take moments, and this requires us to work out some angles. So I think the way we've settled when we do moments, I'm going to do moments around the base, is to say, okay, this is the object, the rigid body is the phrase I often refer to that we're talking about. So if we want to calculate moments, we need to know the force perpendicular to the rigid body. So for example, this weight, I need to know its component perpendicular to the ladder. This, I need to know its component perpendicular to the ladder. And this, I need to know its component perpendicular to the ladder. I also need to know the distances, which are nice and easy, because that's at 3.5 meters, and that's at 7 meters. We're told that in the question. So go on, see if you can work out the angles here, and write me an expression for moments about the base. Don't forget the distances. Okay, so it's the force, the perpendicular component of the force times the distance. We don't need to worry about these forces because we're taking moments about this point here. So pause and have a go at that. Okay, so I did work out the angles down here, but don't need them. So I've got clockwise moments, so that's pulling it this way. And there's two of those, there's this one and there's this one. So that's 11g cos 60 times 3.5 and f cos 60 times 7. I've then got anti-clockwise moments, which is this one here, pushing it the other way, 35 cos 30 times 7, and then a little bit of algebra gives me the value of f. Do you remember we said because it's in limiting equilibrium, f is equal to mu times the reaction here, which in this case is actually n, and we know n is 35, so I'm going to use the exact value there. So I've got the exact value on my calculator, so I'm going to do that divided by 35 to get the coefficient of friction. And it's always reassuring, that should be a value between 0 and 1, and there we go, we've got that. Oh, I'm in school. Okay, so that, I'm hoping, was a fairly straightforward ladder question. Ladder questions are hard, but remember the sequence. Resolve, resolve, moments, and you're always going to get marks, even if you don't get to the end. So let's look at a more complicated question. Okay, so this is the sort of question that I'm talking about here. It's still a ladder, and actually this question is not in the motorbike book. This is in the Stats 2 book. There's an electronic version of that on OneNote, but you may just want to screenshot it. Page 145 anyway, question 7. And here the ladder is resting on a cylinder. The cylinder is smooth, so there's no friction to worry about here, but the ground is rough. The ground is rough. So we're going to have a go at this question here. So you might want to do a quick sketch. You've got to think about the reaction forces, because that's where this one is different. Remember, the reaction force is always perpendicular to the surface that the thing is sitting on. So have a go at sketching a diagram for this one. I'm going to do the same. Okay, so here's the key difference. At the base, it's all normal. We've got a normal reaction force, and we've got a force of friction, because the only way this ladder is going to go is that way. There's no way the ladder's going to slide that way, because this is a smooth cylinder. So the friction is going to react against that, it's going to resist that force. Okay, but here's the difference. The normal reaction force here is going to be perpendicular to that cylinder, and the angle here is going to be a right angle. So it makes this actually a little bit simpler when we come to taking moments. So when you've got the ladder sitting on a cylinder, the reaction force is already perpendicular to the ladder, because the angle between a radius and a tangent is a right angle. And if that's 35, then that's 35, and this angle here is 55. Not the whole angle, that's a mistake there. That angle there is 55. So, so let's go through those 3 steps. So firstly, let's resolve vertically. A little bit more complicated this time, because we've got that going vertically, but this force isn't vertical. So I've got to do n cos 35 to get the vertical component of it. So they're both going up, and 20g is coming down. Similarly, a bit more complicated with the horizontal resolving. Can ignore that and can ignore that. This is going one way, and this is not going vertically, so I've got to do the vertical component of that, which is n cos 55. Okay, what about the moments? Well, if I take moments about the base, I've actually only got 2 forces to worry about. I've got this force here, so I need to work out the angle to make that perpendicular to the ladder. And this is already perpendicular to the ladder, so there's no angle involved here. it's just force times distance. So go on, see if you can write down the moment statement, taking moments about the base. Pause and have a go. Okay, so here we go. So we've got, this is 35, so 20g cos 35 times 3.5, which is the distance, equals n times 5. So you've got this force pulling it clockwise and this force pulling it anti-clockwise, one equals the other. And I can do a little bit of sums here to work out the value of n, and I've stored that value. So it's 112 point something newtons. It's all straightforward. So if I feed that result into the resolving vertical and horizontal statements, I get a value of f. Again, I've stored that. And I get a value of r. So that's just the two statements we had a moment ago here. Now we know what n is, we can plug that value in here and here. Now, the question actually is, what's the minimum value of mu? And we're not told that this is in limiting equilibrium, but if it is in limiting equilibrium, then F is equal to mu r, in which case mu is that number divided by that number. Now, we're not told that F max, F limit might be bigger than that, but it's got to be at least that, because otherwise this will be sliding away. So this is the answer to the question. Having worked out the value of F, having worked out the value of R, we can say what the value of mu is. Now, one extra bit I want to make, one extra point I want to make here, and that's because of the question we've got coming in a minute. If I think about this base here, I've got two forces, haven't I? I've got a vertical force, which we've worked out, and I've got a horizontal force, which I've worked out. And so what you could say is you've got two forces there. What's the resultant force? What's the resultant force? And yeah, we can work that out by saying, right, what happens if you put one force followed by the other? That's the resultant force, isn't it? And the angle here, or we could work out, the angle to the horizontal would be, we could work that out. So go on, just taking the value of F that we've got and the value of R that we've got. I wish I'd drawn it this way now, actually, so let's draw it this way. Tell me what the resultant force is here, both in terms of its magnitude and its direction. And I want the direction as an angle to the horizontal. Okay, pause and have a go. Okay, so hopefully you got that. So yeah, we've got these two separate forces, the reaction force and the friction force, which we could combine to say, right, so the resultant, the combined effect of those two forces is this at an angle of this. So why have I made that point? Well, the last question I want you to have a go at is one that comes from, and I think I've referred to this before, we did an integration question. This is the 5 hardest questions ever in New Spec A-level, and only 25% of people scored marks on this question. So I've attached this one to the email telling you about the video, and I'd like you to have a go at it. You'll note that it says find the magnitude of the resultant force acting on the ramp at A. So that's just what we've done. You will have a reaction force and you'll have a friction force, and it wants the combined effect of those two forces. I mean, this part's nice and easy. Why the reaction on the drum at the ramp acts in the direction that's perpendicular to the ramp? Well, because it's always perpendicular to the surface, and the surface is at right angles to the ladder at that point. That's only true if it's smooth, because if there was friction involved, you'd have the same effect that we've got here. You'd have a resultant force there. but because we're told that the cylindrical drum is smooth, then again it's just like that previous question. So I'm not going to say any more. I'll attach this and the solution to the email. And sorry, I said I wouldn't say any more, and I lied. Just in case you're not clear, we don't know the angle, do we? So don't do shift tan. Just do the trick that we've done a few times now. This is an acute angle. So one triangle it could come from is a triangle like that. Use Pythagoras to work out the hypotenuse, and then just write down what sine theta and cos theta are. So this is one of these questions where we'll have to use sine because we won't know the angles. So if you know the angle, you use cos. If you don't know the angle, you use sine. Right, I'll definitely go now. Take care.